I want you to just take a second and picture standing on a vast, silent expanse of ice. Like it just stretches all the way to the horizon in literally every direction.
And in some places, it's actually thick enough to bury an entire mountain range.
Right, exactly. And when you're standing there, I mean, it feels utterly solid, right? It feels completely motionless underfoot. But here's the thing, that stillness is a total illusion. That entire mass of ice is actually moving.
It really is, yeah, one of the most brilliant illusions in nature. You're standing on a glacier or, if we zoom out, an entire ice sheet. And while it might look like the most static, unchanging landscape imaginable, it's actively flowing downhill.
Just under its own weight.
Right, under its own weight. And it's violently carving the earth beneath it and quietly preserving a record of the planet's past all at the same time.
Which is just wild to me. When I was diving into our sources for today's deep dive, that is what fundamentally shifted my perspective. We think of ice as this rigid, shattering thing, but on a macro scale, it's essentially a slow-motion river.
Yeah, it really is.
But I want to make sure we do this justice. Our mission today is to trace that incredible journey. Like, how does ordinary falling snow turn into a landscape-carving glacier? We're going to decode the climate secrets trapped inside and, separate fact from media fiction regarding the future of these ice sheets.
Wow. And I think it's important to say right up front, we are going to take our time unpacking this. You don't need any science background to appreciate the marvel of glaciology. We're just going to break it down.
Perfect. So just to get a glacier going, the math of it is kind of crazy. It's not just like a really big snowfall. It has to be a localized surplus over decades.
Right. Exactly. It requires a specific climate. Basically, more snow has to fall each winter than melts away over the following summer.
So it's just year after year of buildup.
Right. Year after year, those layers accumulate. And if you look at fresh snow, I mean, it's mostly empty space.
Oh, right, because of all the air.
Yeah, it's just a loose, fluffy arrangement of delicate ice crystals with huge amounts of air trapped between them. So a thick blanket of fresh snow can look incredibly deep, but it actually contains very little water.
So if it doesn't melt, the weight of, say, year 2 compresses year 1. I was trying to visualize this, and it's kind of like packing a snowball in your bare hands, forcing all the air out, but scaled up to the weight of a literal mountain.
That's a great way to think about it. Under that sustained pressure from above, the delicate snow crystals gradually round off and they start to interlock.
Oh, so they change shape.
They do. In fact, some ice crystals literally grow at the expense of others, and this creates an intermediate material. The technical term for it is firn.
Firn, okay.
Yeah, firn. It's granular and partly compacted, so it's denser than fresh snow, but it's not yet true, solid ice. And to officially be classified as firn, it typically has to survive at least one full year buried under fresh snow.
Wow, okay. And then it just keeps getting squeezed as more decades pass. Like, how long does it take?
Yeah, it takes a very long time. Eventually, the sheer weight of all those accumulating layers above just squeezes out virtually all of the remaining air, and that's when it becomes genuine, dense glacial ice.
So where does the air go? Does it all escape?
Well, most of it is squeezed out, but the only air left is trapped in these isolated, completely sealed-off bubbles. And over the full depth of an ice sheet, this transformation from fluffy snow to dense ice can take many hundreds of years.
Hundreds of years. So like a single snowflake falls on the interior of an ice sheet today. It's delicate, it's recognizable, but it might not finish its journey into solid glacial ice until after you and I are long gone.
That's exactly right.
And once it does, that single water molecule can be locked in the flowing ice for thousands of years before it ever touches the ocean.
It really requires a completely different perspective on time.
It totally is, which makes the physics of it so strange to me. So we have this dense, massive, solid block of glacial ice packed over centuries. If I drop an ice cube on the floor, it shatters. I just don't fully grasp how a solid mass can flow downhill without just cracking apart into a million pieces.
Right. It seems counterintuitive. But it comes down to what is happening at the molecular level. Under the immense sustained stress of hundreds or even thousands of vertical meters of ice piled up above it, the ice deep within the glacier actually becomes plastic.
Okay, but plastic? Because I think of, a synthetic water bottle when I hear plastic.
Yeah, that's a common confusion. In physics, calling a material plastic just means it's malleable. It permanently deforms and changes shape over time without cracking.
Okay, so it's not breaking, it's just bending.
Yes, and we call this internal deformation. The water molecules in the ice's crystal structure are under so much pressure that individual layers can slowly slide past their neighbors without breaking their bonds entirely.
That is wild.
It is, and this internal sliding is what allows the glacier as a whole to gradually change shape. It flows from the high elevations where snow is piling up down toward lower, warmer elevations.
Okay, I get the internal sliding part, I can visualize that, but it still seems like, I mean, you've got millions of tons of ice scraping against solid bedrock at the bottom. Wouldn't that cause so much friction it would just get stuck? Or wait, does that friction actually help it move?
You hit the nail on the head. The friction is actually the catalyst for the second mechanism, which is called basal sliding.
Basal sliding, so sliding at the base.
Exactly. The intense pressure from all the ice above, combined with the friction of grinding against the underlying rock, actually raises the temperature right at the base of the glacier.
Even if the air outside is freezing.
Yeah, even if the air far above is well below freezing, it causes localized melting right there at the bottom.
Oh, I see. So it creates this thin layer of liquid meltwater between the ice and the rock. It's kind of like a car hydroplaning on a wet road, right?
That is a perfect analogy. That thin film of water acts as a lubricant. It allows the entire mass of ice to slide over the bedrock much, much faster than internal deformation alone would allow.
Huh.
Because of this, glaciers that have a warm base and access to meltwater, they flow noticeably faster than glaciers that are, just frozen solidly to the rock beneath them.
Millions of tons of ice sliding on a microscopic film of water. That's terrifying and amazing. But as it moves, it has to be tearing the landscape apart. Because, like, a river cuts a V shape, right? Because flowing water seeks the lowest point of a valley. But a glacier is filling the entire valley floor to a massive depth.
Right, it's nature's bulldozer. It erodes the landscape on multiple fronts simultaneously, and it does this through two main processes. The first one is called plucking.
Plucking, like plucking a guitar string.
More like plucking a weed out of the ground. Meltwater from the glacier seeps into cracks in the underlying bedrock. Then it refreezes and expands, and it effectively grips onto fragments of the rock.
Wow.
Yeah, and as the glacier inches forward, it just tears those rock fragments right away from the ground.
So it's basically stealing the bedrock. And once those rocks are plucked out and embedded in the bottom of the moving ice, they must act exactly like grit on sandpaper.
Exactly. And that second process is called abrasion. Those embedded rocks scour and grind the bedrock, basically smoothing and deepening it.
So it just files the mountains down.
Over thousands of years, yeah. This massive icy sandpaper carves out broad, deep, U-shaped valleys instead of the V shape of a river.
Right, the U-shape. And when those U-shaped valleys are carved right down to the coast and the ice eventually melts, the ocean floods in. That's how we get fjords, right?
Yeah.
Like those incredible cliff-lined inlets in Norway or Chile. They're literally just drowned glacial valleys.
You've got it. And geologists read these features as clear signatures of past ice. It's not just fjords and U-shaped valleys, though. Glaciers also leave behind moraines.
Moraines, what are those?
A moraine is basically a ridge of jumbled, unsorted rock debris. It's everything from fine grit to massive boulders. The ice bulldozes this material forward or drags it along its sides and then simply drops it all in a mound when it melts.
Just leaves its trash behind. And the sources also mentioned erratics, which are those giant boulders sitting out in the middle of nowhere that don't match the surrounding bedrock at all. They just hitched a ride inside the flowing ice from somewhere completely different and were dropped exactly where the ice happened to melt.
Right, they're entirely out of place. And geologists lean heavily on this combination of features. Together, they form an unambiguous fingerprint. When you see them, you know ice was the primary sculptor of that landscape.
Okay, so this brings up a huge question for me. If these U-shaped valleys and moraines are evidence of past ice, and we know glaciers are always flowing forward downhill under their own weight, it feels contradictory to constantly hear about glaciers, retreating. How can something be moving forward and retreating at the exact same time?
It sounds like a paradox, doesn't it? But the paradox disappears when you look at mass balance. You can think of mass balance as the running ledger of ice gained versus ice lost over the course of a single year.
Ah, okay. So think of it like a bank account for you listening. Your paycheck is the fresh snow depositing at the top of the mountain, and your expenses are the melting happening at the bottom.
That works perfectly. High up on the glacier, at colder elevations, snow falls and accumulates. We call this the accumulation zone.
The paycheck zone.
Right. And further down the valley, at lower, warmer elevations, is the ablation zone. This is where the glacier loses mass through melting. Or, if the glacier reaches the ocean, it loses mass through calving.
Calving is when the large chunks break away from the leading edge as icebergs, right?
Yeah, exactly. So you have accumulation at the top and ablation, melting, or calving at the bottom.
And somewhere in the middle is the break-even point.
Right. The boundary where accumulation and ablation perfectly balance out over an average year is called the equilibrium line. If a glacier gains more mass in its accumulation zone than it loses in its ablation zone, the mass balance is positive. The leading edge will actually advance further down the valley.
But if your expenses outpace your paycheck, your account balance shrinks. So the glacier's still flowing forward, like the cash is still moving, but it's melting at the front faster than the flowing ice from behind can replace it.
Precisely. The mass balance is negative, causing the leading edge to retreat back up the valley. And the overwhelming majority of monitored glaciers around the world today are in a state of negative mass balance.
And this isn't just a guess, right?
No, not at all. This is a well-documented trend using standardized measurement techniques all over the globe. They are retreating at a pace that is highly unusual compared to the historical record.
Okay, so if glaciers are in this widespread state of negative mass balance, how do we actually know if this is an anomaly or just, Earth's natural rhythm? Does the glacier somehow keep a record of what the atmosphere looks like in the past?
It does, actually, in a remarkably literal way. We talked about how snow compresses into firn and then solid ice, right?
Yeah, the snowball getting squeezed.
Well, when that happens, those pockets of surface air get sealed inside. They are trapped and preserved as tiny bubbles, layer upon layer, essentially completely undisturbed.
Wait, so scientists just drill down into the ice and pull off a literal sample of old air?
They do. They extract a continuous cylindrical sample called an ice core. By bringing these cores to the surface, they can extract those ancient air bubbles and directly analyze the composition of the atmosphere from the specific year that snow fell.
That is mind-blowing.
It is. They can measure greenhouse gases like carbon dioxide from tens or even hundreds of thousands of years ago.
So we aren't looking at a model or an estimate here. It's a direct physical sample of ancient air. It's essentially an atmospheric time machine. But, how do they date the layers? Like, how do you know which bubble is from which year?
It's fascinating. In favorable conditions, you can count the layers in an ice core almost exactly like counting the growth rings of a tree.
Oh, like tree rings, really?
Yeah. Seasonal differences in snowfall or, the amount of dust blowing around during different times of the year, they leave visible or chemically detectable annual bands in the ice.
Okay, so the sources noted they also use the ice itself to reconstruct past temperatures using something called an isotope proxy. I was really trying to wrap my head around that mechanism.
It's a bit technical, but essentially water contains slightly different atomic variations or isotopes of oxygen. And the heavier isotopes fall out of the clouds at different rates depending on the temperature of the air at that time.
Okay, so the temperature controls which type of oxygen makes it to the ground.
Exactly. So the ratio of those isotopes in the ice acts as a highly calibrated stand-in or proxy. By measuring that specific ratio, scientists can reconstruct the past temperatures at the exact location the core was drilled.
So it can measure the exact temperature at the time the snow fell. That's incredible. How far back does that record go?
Well, the longest continuous ice cores retrieved so far come from the deep ice of East Antarctica. They stretch back roughly 800,000 years.
800,000 years. Preserved one snowfall at a time. That's just wow. And what about the ice cores from Greenland? Are they the same?
They're a bit different. They don't reach quite as far back because snow falls much more heavily in Greenland. So the older, deeper record gets compressed into thinner, harder to resolve layers at the bottom.
I see.
But that heavy snowfall is actually a massive advantage for recent history. Because the annual layers are so thick, Greenland ice cores can resolve individual years and sometimes even individual seasons with extraordinary detail.
So it's like zooming in on the timeline.
Right. They are absolutely perfect for studying abrupt, short-term climate events in our more recent past.
Okay, so looking at those two modern giants holding most of the planet's freshwater, Greenland and Antarctica, they seem to be reacting to the current climate in very different ways.
They operate very differently, yeah. The Greenland ice sheet is losing mass predominantly through processes happening right at its surface. Warmer air temperatures cause increased summer melting, and much of that meltwater simply runs off directly into the ocean. It's a very straightforward mechanism to observe.
You can just see it melting. But Antarctica is vastly larger and way more complex, right? It's essentially two separate systems.
Exactly. East Antarctica sits mostly on highland, well above sea level, and it seems relatively stable. But West Antarctica is the one triggering all the alarming headlines about vulnerability.
Right, because a substantial portion of West Antarctica rests on bedrock that is actually below sea level.
Yes. Its ice sheet is in direct contact with the ocean through enormous floating extensions called ice shelves. And these shelves act like structural braces. They literally hold back the ice sheet on land, slowing down its natural tendency to flow into the sea.
So if warmer ocean water reaches underneath those floaty shelves and melts them, they thin out and lose that bracing effect, like knocking out a support beam. And then the ice behind it flows into the ocean considerably faster.
That's exactly what's happening.
But the really concerning part in our sources is something called marine ice sheet instability. Can we walk through the actual mechanics of that? Because it sounds pretty intense.
It is intense. The mechanism hinges entirely on the shape of the bedrock beneath West Antarctica. Instead of sloping upward as you move inland from the coast, the bedrock actually slopes downward.
Wait, so the further inland you go, the deeper the bedrock gets below sea level.
Exactly. And the point where the ice sheet finally lifts off the bedrock and starts floating is called the grounding line. If the protective ice shelf thins and that grounding line is forced to retreat inland, it moves into deeper and deeper water.
Because of that downward slope.
Right. And because the ice is thicker in that deeper water, it exerts more outward pressure, which accelerates the flow.
And more of the ice face is exposed to the warm ocean water.
Which accelerates the melting even more. It creates this self-reinforcing feedback loop. The further it retreats, the deeper the water gets, the faster it flows, and the faster it melts. This is marine ice sheet instability. And the Thwaites Glacier in West Antarctica is a prime example of this mechanism in action.
Okay, I want to push back on this just a bit because we see Thwaites referred to constantly in the media as the doomsday glacier, which, those are very heavy, panic-inducing terms. For anyone trying to filter through the noise here, how much of this instability is happening right now and how much is just theoretical modeling?
That is a very fair question. It is vital to separate what we observe from what we model. We know with absolute certainty that mass loss is actively happening right now.
Because we can measure it.
Right, we have decades of satellite measurements of ice elevation and gravity, direct field measurements, repeat photography. The thinning of the ice shelves and the retreat of the grounding lines in West Antarctica are indisputable facts.
The instability is active, so what is the uncertain part?
The genuine scientific uncertainty lies in the pace. Modeling exactly how quickly a massive fractured block of ice will respond to complex ocean currents and atmospheric changes over the coming decades is incredibly difficult.
So we know it's happening, we just don't know exactly how fast it's going to happen.
Exactly. Translating current mass loss into a precise, confident projection for sea level rise, say 50 or 100 years from now, it requires navigating a wide range of probabilities. Reputable scientific bodies are always upfront about this margin of error.
It's a balance. We can't dismiss the reality of the mass loss, obviously, but the extreme worst-case timelines push in headlines are often the lowest probability models.
Right. The physics of marine ice sheet instability are sound, and the retreat is documented. But the Earth system has many interacting variables, and forecasting the exact speed of collapse is an ongoing scientific challenge. We really need to avoid both unwarranted alarmism and unwarranted dismissal.
That makes a lot of sense. Man, this completely changes how we'll look at ice. I mean, from a single fluffy snowflake to a continent-crushing river carving fjords, the stillness of a glacier is really just a trick of our limited human lifespan.
It really is.
It is a constantly moving landscape and just an undeniably honest archive of the planet's history. But I want to leave you with one final thought to mull over. We talked about how those deep ice cores perfectly capture the atmosphere from hundreds of thousands of years ago in those tiny air bubbles.
The atmospheric time machine.
Right. Think about the snow falling on the high, quiet interior of Antarctica right this very second. It is trapping today's air right now. What exactly will the bubbles we are laying down today say about us to whoever or whatever might drill an ice core 10,000 years in the future?
That is quite a thought to end on.
It really is. Thank you so much for joining us on this deep dive. We will catch you next time.